In this derivation, I'm going to show the electric field due to a straight distribution of charge. A couple of initial conditions, which are usually the most important parts of doing these types of problems. For starters, I've got a distribution of charge over here that's linear, and I'm going to treat it like a point charge, and I can only do that if I divide it up into a tiny little bit of charge that I can call a differential of charge. And that's going to be some distance away from point P, which I can show with this pink line. That creates a right triangle with some important features to it. For starters, the separating distance between the distribution of charge and point P is r. I can say that d is the distance between the distribution of charge and point P. And I can say that y, more generally, is the distance from the intersection or the origin, the intersection of D with the y-axis, or the distance that the distribution of charge is from D in a straight line. So I can see that I have a right triangle here. I'm going to call this angle theta. And my goal is to divide up this linear distribution of charge into a whole bunch of little differentials of charge that each produce some sort of electric field here at point P. And if I draw like a sampling of them in, you can see that they're all going to be pointing to the right. We assume for a positive test charge that these positive charges along that linear distribution would be all pushing to the right. The y components are going to cancel each other out. And so therefore, I'm only going to be left with an x component of the electric field. That's important. Let's go ahead and start with our definition of linear charge distribution lambda. We can say that generally speaking, it's Q over L, the total charge over the total length. And we do these for all these types of problems. We can also say that lambda is equal to dq over dy, where dy is this tiny little length right here of the total length of the distribution of charge. So this piece is important as a starting conditions. You will see how we're going to substitute that later. The next thing that we have to deal with are some distance, some analysis, or let's take a look at how to describe r in terms of d and y. You should be able to see that the Pythagorean theorem is c squared plus a squared plus b squared, and therefore we can say that r squared is equal to y squared plus d squared. That's important. Furthermore, we can say that r is equal to the square root of y squared plus d squared. So I've just taken the square root of both sides. Finally, so this piece will become an important substitution that we make, so I'll put that in pink when we talk about distances. And then finally, let's look at the trigonometric piece, cosine of theta. Cosine of theta, by definition, is the adjacent side over the hypotenuse. It's that ratio. The adjacent side, in this case, is the dimension or the linear distance d, and the hypotenuse is y squared plus d squared to the 1/2. And so we can see that this piece is also going to be important. And so the ones that I've drawn in blue, pink, and green are all substitutions that we're going to make fairly early on. Let's go ahead and start. More generally, I'll write this off and to the right. You know, this is given to you on your equation sheets, but we know that the electric field due to a point charge is K, which is 1 over 4 pi epsilon naught times Q squared, Q over R squared, if R was the separating distance. And so now I can say that the component or dE sub x, the component of the electric field in the x direction, is equal to K, which is 1 over 4 pi epsilon naught, times dq, the differential of charge, or the tiny little bit of charge, over r squared. I'm going to use lowercase r because that's what I used here in my right triangle, times the cosine of the angle theta. So this is my starting point, and then I'm going to make a whole bunch of substitutions. I'm going to substitute cosine theta here. I'm going to substitute for r using this guy, and I'm going to substitute for lambda. I'm going to ultimately say that, I'm going to substitute for dq. I'm going to say that dq is equal to q over L dy. is equal to dq. And that's what's going to get substituted in here. Let's go ahead and make all of those substitutions in one fell swoop. So I can say that the differential of the electric field in the x direction is equal to the constant 1 over 4 pi epsilon naught times q over L dy. That's what I've substituted in for dq. R squared is equal to y squared plus d squared. So that is here, y squared plus d squared. And then finally, the cosine of the angle theta is equal to d over y squared plus d squared to the 1/2. So I've gone ahead and made all of those substitutions. I can combine some terms here, but I'll do that in the next step. What's important to see, as usual, is we're going to integrate both sides. We're going to integrate this side, and we're going to integrate the right-hand side. So we add up all those little distributions of charge and the resultant electric fields. I have to describe then my limits of integration. I'm going to call the bottom end of this negative L over 2, and the top end of this positive L over 2. And so this becomes negative L over 2 down here and positive L over 2 there. In my next step, once I've integrated all of this, this just becomes E, the x component of the electric field. My constant is 1 over 4 pi epsilon naught. But I'm going to make some substitutions. Q, I need to bring out my constants. Q is a constant. That's not changing, the charge over the whole piece. L is also a constant. That gets pulled out. And D up here is also a constant. That's not changing, so I bring D out. And I'm left with, I should have broken this up here. So let me kind of make a substitute. Let me correct that. I just wanted to leave the D here. And then over here, I have dy over y squared plus d squared to the 3/2. And I can't forget that I haven't dealt yet with the integration over on the right-hand side, which is going to be pretty tough. So I've arrived at this point, and I have to integrate everything over on the right-hand side. And I'm going to write this off in blue on the right here. This is kind of inside cover of the calculus textbook type stuff, or perhaps in one of the appendices. I have a general integration of the form a squared plus x squared to the 3/2. So dx over a squared plus x squared to the 3/2. When you integrate that, you get x over a squared times a squared plus x squared to the 1/2. This is something that most people are not going to know how to get from here to here, what I've written in blue. And so that is something you will simply have to commit to memory. And our goal then will be to integrate all of this stuff right here, paying attention to what I've just written in blue. So this is really the tough part of this problem. The left-hand side doesn't change. It's the x component of the electric field. And I get Q and D in the numerator. In the denominator, I get 4 pi epsilon naught L. And now I have to integrate this thing. And if you pay attention to what's been written in blue, in the numerator, I get y. And in the denominator, I get d squared d squared times y squared plus d squared to the 1/2. And this d squared, the two d's here cancel out with this d here, and now I can pull that d out. I still have to evaluate this between negative L over 2 and positive L over 2. So our next step then is to say the x component of the electric field is equal to Q over 4 pi epsilon naught dl. And now I'm going to substitute in for the numerator. I'm going to get L over 2 over, in the denominator, y squared plus d squared to the 1/2. But I have to substitute in for y squared, so I can't do that. That's going to be L over 2 squared. L over 2 squared. I'll put another set of parentheses there. I'm going to subtract from it the lower limit of integration, so I get negative L over 2 here. And everything is the same, except I get negative L over 2 squared plus d squared to the 1/2. So what that means now is that L over 2 plus L over 2, let's go ahead and take the next step. E to the x is equal to q over 4 pi epsilon naught d times L. L over 2 plus L over 2 is just L. And in the denominator, I'm going to get L over 2 squared plus d squared to the 1/2. L over 2 squared plus d squared all to the 1/2. And now you can see that this L and this L cancel each other out. My final expression then becomes e to the x is equal to q over 4 pi epsilon naught times L over 2 squared plus d squared all to the 1/2. And that is our finishing point. That is how we define the electric field due to a linear distribution of charge. Now wait a second here. I forgot this d here, so I got to make sure that I don't forget it here in my final expression. So I've just added that piece. There's one last thing that I want to do. Let me move this guy a little bit up and out of the way. That's our final kind of ending point. Let's do these last little pieces which show an application of limits. What happens if the length L approached infinity? So we're basically trying to describe what happens to the x component of the electric field when we take the limit of that expression as L approaches infinity. It gets very long, infinitely long. And so when we do that, we can see that the d doesn't matter, and I just get L over 2 squared square root, which is just L over 2. They effectively cancel each other out. And I'm left with something that looks like this. I get q over d, I won't forget that this time, over 4 pi epsilon naught. And by the way, even though I didn't forget the d, we said that the d doesn't matter. This d and this d don't matter because L is changing, it's approaching infinity, and d isn't. So I'm going to get rid of that I just put in. I get q over 4 pi epsilon naught, and then I get just simply L over 2 squared. That gives me an L here and a 2 in the numerator, right? L over 2, but I'm already in the denominator. Now I can reduce this, the 2 and the 4, and my next step then looks like this. I basically get q over 2 pi epsilon naught L. If I wanted to, I can say that q over L is equal to lambda, so I'd get lambda over 2 pi epsilon naught. And we can see that that is the result of L approaching infinity. What happens to the electric field if in the x direction, if on the other hand d approaches infinity? So let's take the limit of that expression as d approaches infinity, and let's go ahead and write down our starting point. We get L over 2 now not becoming not important, so we get q. So now in this case, this isn't changing, but d is approaching infinity. It's dominated by the variable d. I get d times 4 pi epsilon naught. D squared to the 1/2 is just d, but then I have a d squared, and I get q over 4 pi epsilon naught d squared. Well, this is just a point charge. And so we can say then that as the distance d approaches infinity, the expression begins to resemble that of a point charge.